Hello students, welcome back. We have one more problem here, and that is the estimation of sample size. And this one is relatively important. Sample size problem is not that important for means, but for proportion it is a little bit more important. And the reason why it is a little bit more important than the case of mean will become apparent as we go through the problem. Alright, here we go. A political research team is preparing for an opinion poll of an upcoming referendum through a simple random testing. If they want to obtain the point estimate of the referendum within the margin of error of 2.0 percentage point with a confidence level of 97%, what is the minimum number of sample size? Here, if they have a good idea, approximate expectation of what percent of the people will be for the referendum, then maybe you can use that. But here in this problem, there's nothing there. So where do we put our base? That is a question that we have to answer. Let's begin with a picture. Okay, horizontal line. And then we have a normal picture like this, normal approximation. And here, I'm afraid I have no idea what this is. So the proportion P is unknown here. And that creates a problem because, do you remember the SE formula? SE equals to square root of P1 minus P over N. We need N, but we don't know P either, and that's a problem. Okay, let's continue. We want 97% in the middle, so okay, 97% in the middle here. Monochrome is not very good. So that means the other 3% come from here, which is 1.5%. And also there, 1.5%. And then we have left-hand side endpoint and the right-hand side endpoint. And we can use the z-score formula, end minus center over SC. But end minus center is actually this. Right-hand side here, minus center, is actually this distance. Or equivalently, this distance too, because of the symmetry. So the margin of error of 2.0 percentage point is coming right here. I don't have to know the center. I don't have to know the right-hand side endpoint. All I need is this distance being 2 percentage point. By symmetry, of course, this distance here to the left is also 2%. See the idea here? Margin of error. That's the biggest error you can get within the confidence interval. So you're going to use the center here, the observed proportion as your point estimator. And then the biggest possible error within the confidence interval is going to all the way to the endpoint. So the radius of this confidence interval is the margin of error. Okay, so much for this lousy picture. Let's go back to my notebook with a little bit better picture now. Okay, here is a little bit better visualization. So we don't know the center here, but we do know this endpoint is center plus 2 percentage point, center minus 2 percentage point. So this radius is 2 percentage point, the margin of error. So what do I do here? Z-score is end minus center over SE, right? And that is, end minus center is this radius, so this is margin of error. over SC, P1 minus P over N, and the sample size N is the quantity we are looking for. And that's approximately equal to the z-score that we want. Oh, by the way, what is the margin of error in this case? Margin of error? That's 2% point, wasn't it? And z-score is gonna be, what's the z-score here? Where's my z-table? Okay, and I need 1.5%. So 1.5% right here. Do you see? Negative 2.17. It's in negative 2.1 row and it's in 7 column. So negative 2.17. You see? To the left we have 1.5%. 1.5% to the right, 97% in the middle. So look up 1.5%, and that was negative 2.17. From here, can you solve this equation? Oh boy, we have a problem. N is the quantity we are looking for, but I have another problem here. What's P? Well, to make a long problem short, if you have a reasonable estimation of P, if the problem gives you, then you can use it. Otherwise, you have to use 0.5, half. Why? Because that maximizes the standard error. We're going to talk about that maximization a little bit later. For now, let's just work on it symbolically. So it goes like this. Square root of P, 1 minus P over N. Actually, what am I doing? It's going to be easier to flip over this N. So 0.02 square root of N, and then let's keep the other square root. Come on. Oh, come on. All right, I got it. Like this. Okay, that's a z-score. What did I do? This is division by square root of N, so I flipped it over. See this? Okay, let's flip over everything, and this is what I'm gonna get. Square root of N is approximately equal to negative 2.17, which is, oh, excuse me. If I'm gonna use negative 2.17, I'm moving to the left. So this margin of error should have negative sign. Of course, with this, you have negative quantity as a square root. That doesn't make any sense. So in the end, you have negative, and then you have another negative there, so you can actually discard those. So it should be the actual positive 2.17. Sorry about that. And then times square root of P, 1 minus P, the standard error, and then over 0.02. And this is approximately equal to, let's see, what is 2.17 over 0.02, approximately speaking, is 108.5 times square root of P, 1 minus P. Okay, one more to do. This is square root of N. How do you get your N value? It's easy. This is 3000 level course, so that should be easy to everybody. Take square of both sides. So N is approximately equal to 108.5 squared, and then P 1 minus P. There you go. That's your n value. But you see, you want to keep your margin of error within something, so n value has to be at least greater than this thing. Or more precisely speaking, I'll have to use this notation, greater than approximately equal to, okay, because nothing is accurate in statistics. This is really hard to read. Let me just keep greater than equal as before. So n should be at least greater than this quantity. So this quantity should be overestimated so that n is, sufficiently bigger than all those. And that's where 0.5 is coming into play. How do you maximize this? This is quadratic expression. You can use calculus if you want to. Take the derivative, set it equal to 0 to find out the maximum value. If you do it right, you're going to get 0.5. So that actually is greater than or equal to the special case. P is 0.5. So that this is also 0.5. In elementary statistics class, I just tell students to just replace P equals 0.5 and go from there. But here we have 3000 level course, so everybody can follow these kind of symbolic computations, okay? And then everybody can do this optimization. What's the maximum of this? So we want really overestimation. And if you plot this P1 minus P, it's going to be a parabola, upside down parabola. It takes a maximum at 0.5. So that's where you're getting P equal to 0.5. And then if you do your computation, you're going to get this value. It turns out you get 2943.06. And it should be higher than that. So 2944 will do. But then again, everything is approximation in statistics. So I'd rather go for 3000 or higher. That's reasonable. So 3000 or higher. Make sense? Still, that's actually a classroom example. Nothing comes close to reality. In reality, 3000 is not going to be enough. You need significantly more than 3000. Why? Because you have to count for non-responders. How many non-responders, or what proportion of non-responders do you expect in any kind of poll? That's related to poll history. So depending upon what kind of district you're going to, what kind of neighborhood you are going to, you have some history of non-responders, and based upon that, you set up appropriate polling schedule. And that's something completely outside mathematical realm. So in math classes, we don't consider that, so we'll just stop at 3000. But in reality, it has to be much bigger than 3000. For example, if you're going into a neighborhood where a lot of people, really humongous number of people, choose not to respond, say, for example, a third of the people just don't respond, in that case, you want to get something like 4000. So that even if you lose 1000, you still have about 3000 there. But if you're going into some other district there where most people are expected to respond, in that case, you may go down to say 3300 or 3500 and things like that. But in any case, whatever threshold we get in the classroom example is just ideal case. In this particular example, we have 3000 people, and that's coming from setting up an equation but plugging in special value p at 0.5 for appropriate maximization. Okay, so much for sample size example. It took a long time. Okay, that concludes section 5 and this module, module 9. See you next time.